So today is lecture 6, and we are going to learn about at least two different technology on how to treat contaminated groundwater ex situ, means outside the aquifer. So the number one design which is most popular is a carbon adsorption, where we use activated carbons in a big tank, and you pump water through it, and then you treat most of the um, pollution that way. And the second one, which is mostly air stripping tower, there you remove most of the pollutants which are volatile. There you pump contaminated groundwater, at least spray on a tower, and then pump air from the bottom. That way the volatile compounds can strip out of the water. So these are the basic two principles we'll learn, and we'll learn how to design them. At least there's some design calculations. Before that, we have some announcement. Homework 2 is due next class, not next class. Oh, I keep making that mistakes. That's Tuesday. So next Tuesday via CCLE. Quiz 2 is next Thursday. So that's 1 week from now. That's based on lectures number 4, 5, 6, 7. That means everything before that quiz day. And also this is not inclusive for the entire quarter, in the sense everything that was part of quiz 2 is quiz 1 is not going to be part of quiz 2. So you are being tested for everything that we cover after quiz 1. So 4, 5, 6, 7, those are the 4 lectures. So that means we will cover up to lecture 6 today, and lecture 7 will be next class. Project topic is due today, but I'm just going to, this is a more like a fluid. And the whole idea is you have to form a group and start a Google Doc, write whatever you think, you get full credits. So it's really not, it doesn't mean to be like a homework where you have to have a correct answer. This is more like a discussion. So first, at least create a Google Doc, write your team members' names, and write a titles, write a sum, whatever you want to do, at least what you think about it, because I'll give you feedback. That way you can refine the topic. Office hour, so far we have not have any office hour, partly because we didn't have, or I didn't feel like there was office hour needed for the homeworks we gave or the projects. But I do meet meet many groups individually because they set a time for to discuss the project. So I'm always going to do that, in the sense I'll always have individual group meetings or group meeting office hours by email. But I'll also set from now on every week at least 1 hour so that anybody can join during that time and discuss about just in class and any other. I think those are valuable. So that's why these are the two options. So let me create a poll just to see which one you prefer. Let's see this office hour. Say office hour. So option is Monday 2 to 3. Let me just see how many of you are available at different times. I try to not have office hour the same day as class, so that you have at least some times to think of the materials. Okay, so let me put this poll now. See, let me know which times works for you. So 2 options is there. Monday 2 to 3. Again, this is just, you can always meet me any other times as long as you send me email as a group. So this should not be a constraint. If you don't meet on the time we are going to choose, it's still okay. Just want to make sure that who has class at that time. I guess I'm going to close the poll in few seconds. 26 of you so far responded, and I'm going to share the results. So most of you, I mean, it's not like not 50 of students are here. So whatever we have, majority of you prefer Monday. So Monday 2 to 3 p.m. will be our office hour. So that's because we have 73% chose this. But you can, again, as I want to make sure that you can always meet me anytime. Just send me email which day you prefer, then I'll tell you which time I am available for that day. All right, so from next week, let's say next week we'll have Monday 2 to 3 as office hour. I'll also remind you. And again, this is optional. You don't have to come if you don't want to. This is just I'll be there available. I'll set my time for to meet for that specific time. All right, so project topic is due today. I just give you one day extension just in case you have not formed your group. If some of the students who are not really sure which group you are in, send me an email. I'll put one of those group. I already have 4 or 5 groups send their Google Doc link. I have not seen them, but at least I know that you have sent. That's all you need. I'm not really for this project topic. You get credit just by sending that link, because I'll give you feedback. Then we'll continue to update that one. And that project topic should have that Google Doc should have at least title and the scope and all the group members' name. That way, I know that all students, at least in that um, group, have a um, 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 at least they discuss with each other. Again, it's not too late to join a group. It's only when already outline is done that's too late to switch a group, because you already discussed that outline um, on every specific part of the project. All right. So, any questions related to topics or any forming group? If you have not been part of a group and you are right now in the class, you can just either use Campusware to send me a message that you are not part of any groups, and then I'll put you in one of the group where they still have some positions and based on your interest. Okay, all right. So let's get to today's topic quickly. As I said, today we are going to learn about Situ treatment technology, at least 2 of them. One of them is activated carbon, which is very popular, and the second one is air stripping. There's a big difference between them. They don't really, you don't use the same thing or both of them for the same type of pollutants. Mostly air stripping tower is for volatile. Um, and granular activated carbon is mostly for organic pollutants. Organic pollutants. And most of the groundwater pollutants are organic. Again, organic can be volatile. It's not necessarily. In fact, many of those solvents that we use are organic and they are also volatile. Um, um, understand the what you do is you understand the principle behind both technology, and then you'll do some design calculation. That way, anytime you use those in remediation projects, you know exactly how to make those calculations. So these are the questions. We'll solve some questions so that you know how to do it. And the homework 3 has exactly same questions. So you should be able to solve homework 3 based on this class. Okay, so let's have a recap what we have learned, how far we have come in this class. First, you know different rate constant, okay, or at least the properties of different pollutants, which will enable you to make many calculations. Okay, so for then last class you learn how to extract groundwater. Part of the ex situ treatment technology means you have to extract groundwater at the contaminated locations. So now you know what's the capture zone, how much you can, how much pumping rate should be to capture that pollutants. Then you also learn from the last class how much oxidants is needed to treat a pollutant if oxidation is one of the technology. And then also you learn choice of different technology based on what different types of property you have. For instance, volatile contaminants you will have to use, or it's more preferable to use air stripping because it doesn't produce any kind of solid waste. It produces only gas, and then gas can be captured and removed. So these are the different technologies. Just a summary: dig and dump, where you have a polluted soil, and then all you have to do is dig that soil and dump in landfills. But the area is very big, then you cannot use it because it's too expensive to dig a large amount of soil. Then if you think of advanced oxidation, this is essentially you destroy the pollutants completely by using oxidants. And then that means this method requires lots of chemicals for you to add into that groundwater to treat it. So one thing to the positive side, positive part of this technology is it's very specific. That means you can destroy many pollutants, you can control them. And the negative side is the oxidant itself can destroy or decompose many other organic pollutants and produce harmful byproduct. And then also it's a chemical treatment. That means you have to continue to add lots of chemicals. Air stripping, which is require volatile pollutants to be stripped out of water, which is very efficient in that system, and then it doesn't produce much waste because you are making the gas out of the water. But then you have to capture that gas because you don't want them to evaporate or to release to atmosphere because that's air pollutant now. So some method is needed to capture those gas. A lot of times they use actually activated carbon treatments to remove those gas, and then either they burn it or they do other processes. Then carbon adsorption, which we are going to learn today. So these two, the bold colors, those are the things we are going to learn today. What we are not going to learn, which is also part of the ex situ treatment technology, is membrane treatments. Membrane treatments is a very itself is a different class. There is a undergrad class on membrane, so that's why we don't really go details about it. But just know that membrane can remove any ions, most of the pollutants, because it's non-selective. All it does it's permeable to the water, and many pollutants cannot pass through it. But it plugs, so that means it's expensive to continue around membrane for longer time. Then the ion exchange regime, which is basically works with ionic pollutants because you have um, ions can be replaced with another ion so that the charge is balanced. So this mostly works for heavy metals because they are ionic. So instead of copper, it captures the copper and release sodium. Sodium is non-toxic, so that means it's more efficient in that way. But then again, disadvantage is that ion exchange resin, you have to replace that resin more and more, regenerate. Bioremediation rarely used as a ex situ, but it's also similar process. But you will learn that bioremediation more as an in situ treatment technology later in this class. Thermal incinerations is never a recommended technology for liquid water because you evaporate most of them. But sometimes when you want to capture salt and other, that thermal method is probably one of the efficient method, but it's very energy extensive. But a lot of times thermal incineration is used to destroy the solid waste that you produce, like activated carbon. So these are different. As a whole, you should be able to understand the principle. So the quiz question, typical quiz question on these will look like this. So let's say this is a quiz questions. And here I ask, which of the following treatment method won't work to remove benzene? Okay. So benzene is organic pollutants. You at least know we have learned it many times. Then just think of whether which one of them is not going to work. You have a 30 more second to answer. You can chat with each other if you want to. It's fine because this is a discussion. So in the chat window, you can ask these questions. Somebody can answer that. That way, you know how to come up to the conclusions. Okay, so I'm going to close the poll in 5 seconds. So already 1 minute over. Okay, all right, so end poll. So yeah, the results, as you see, it's kind of distributed. No, the majority chose choice D, 58%. Then 25%, 8%, 8%. All right, so let's see how to approach these questions. When you have this kind of question, just first think of, what is this? Because you have to think of this. I didn't give you the methods or the thermodynamic constant. So that means you have to think of them, at least search. So first is air stripping. Is benzene volatile? If you search, it says yes. It can evaporate. So that means air stripping would work. Okay, so that is not the solutions. Advanced oxidation can destroy many organic pollutants. So the only reason it doesn't work is if that pollutant cannot be oxidized. So most of the organic pollutants, just organic, like this carbon hydrogen, can be oxidized. Okay. The only thing that cannot be oxidized is like, let's say, the carbon fluorine bond. Okay, so those are very strong. That's not easy to destroy. So very persistent pollutants. So that means, advanced oxidation can also work. Carbon adsorption is organic pollutant. It can adsorb carbon. So there's no problem in that. Ion exchange, think of this one. If you see what is ion exchange means, that it exchange an ion with another ions. So now you have to think of, is this ionic? If you see in this particular compounds, I give you a structure, there is no ion here. It doesn't say anywhere plus or negative ions. So that means there is no ion for it to have exchange with another ion, right? So this is another way to rule out other options. So the right answer is ion exchange. Okay. All right. So
wait, sorry, could you?
Yeah.
Could you restate how you know that carbon adsorption works? Like what the general question you would be asking yourself to determine if something can
So
be.
I would go back to here, right? So anything carbon adsorption, anything that is hydrophobic or has carbons, more number of carbons, it will adsorb. So if you see over here, it has 6 carbon. It's very hydrophobic now. So that means it should be able to adsorb. Let's say I gave you another formula, CS3OH. Okay. This is the case. We have just 1 carbon, right? Methanol is just 1 carbon. So how much it can adsorb? Well, not much, because just 1 carbon. And OH makes it also hydrophilic because it's a hydrogen bonding. So it's extremely water soluble. That means it's not going to work with a carbon adsorption, partly because highly soluble. Also, it's not very hydrophobic. So now question is where methanol will work. Methanol is volatile, so that means air stripping would work. Advanced oxidation, as I said, anything can be oxidized, most of the carbon, so that's fine. This is also going to work. Advanced oxidations. Ion exchange, this is not ionic substance. If you think up to the only way it can be ionic would be CS3O minus, but that's very rare. The affinity of that hydrogen is so strong that it's not going to be deprotoned. You never see that substance like that. So this is not going to work because this is not ionic. So I think what we can do is um, in the homework 1 question, or you see a lot of this chemical name. So see their structure, and you can ask these questions on campus where how do we know this one, which one would work? It's just like a discussion. Just put a questions, and we'll have discussion on that. That way many of you learn from it. So pick any pollutants from the homework 1 or from the other handouts, and just post it on campus where, and say which one you think would work, and then we'll discuss whether yes or no, and then we'll say which one is most likely will work. And so the more practice you'll have, you'll also get that um, get that right. But mostly, as you see over here, air stripping, it has to be volatile. Carbon adsorption, it has to have carbon, otherwise it's not going to stick. Um, and advanced oxidation, as I said, it has to be oxidized. So you have to think which one oxidize, but most of them will be oxidized. And it says highly water soluble are more preferable because you'll mix that oxidant, so that means it's going to be efficient. Ion exchange, it has to be ionic. The threat over here, So this particular slide can help you make that decision.
Okay, thank you.
All right, so let's get to carbon adsorption technology. So again, carbon adsorption means you have, this is something used in at home. If you have a water filter, it is carbon adsorption. If you, a lot of times you finish that one, you throw it, and the cartridge, break it, cut it, and see what is inside. Because anyway, you're not going to recycle them. They are not, you're dumping into, at least they are not taking it out. So you can break that Brita water filters and see what is inside. You'll see just carbon. And many times it claims that you can remove lead, it can remove other things. Then you can see what exactly to remove lead. Lead can actually absorb most of organic. Any organic carbon, lead can absorb on it. So activated carbon is very good at binding lead. The reason is, if you see over here, most of the activated carbons is made of graphite-like structure. So graphene or graphite, it's like a ring structure like here. So those are hydrophobic. That's where most of the organic sticks. But then you have also at the edge, you have all these functional group. This functional group is ionic, means it can, for instance, here carboxylate. That means it can be COOH. That could be, this is the structure. And so this H can come out. So there is a negative ion. So that's where metals, let's say copper or lead, can bind. So these functional groups are very good at also binding some of the metals based on whether it's protonated or deprotonated. Mostly carboxylic group, not every other. Double bond O is not really can form any other bond. Amine group like NH, something like here, that's this one. That hydrogen, because it's the nitrogen hydrogen, that's the difference in electronegativity. That's where hydrogen can be replaced. In OH, it's very hard to replace, but sometimes OH itself as a whole can be replaced with something else. But the point here is that you have this functional group that also binds some of the ionic substance like heavy metals. But now mostly the adsorption is because of by majority this entire area, hydrophobic. It's called pi electron, so that's a hydrophobic adsorptions. Okay. And these structures are formed when you burn any kind of a biomass or wood biomass at very high temperature. If you think of how the wood structure, cellulose structures are, you will see these rings are there. So these rings are kind of fused after high heating. So that's the thing. It has very high surface area, but when you burn any organic or wood, it doesn't normally have high surface area. So you have to activate it. So learn what does that mean about activations. But what's the limitation of carbon adsorption? Any adsorption technology is a surface active treatment technology. Means you have a surface where things adsorb. That means once you exhaust that surface, it's no longer effective. So that's the reason why most of the time you have to replace that cartridge at home. So same thing also for a groundwater remediation technology. You have to replace the entire tank. And that means it's expensive. It's expensive to produce activated carbon. To replace it, and all the time you're producing this big waste. So a lot of times what people do is they regenerate, means they destroy that adsorbed contaminants by burning the carbon again at high temperature. So before that, just to know how you can produce activated carbon at your home. Anybody can produce it if you have the right structure. So this is how it works. So this is polyetry litter. It doesn't say, or let's say wood chips. Any kind of organics. Okay, so organic biomass or feedstock. So you carry them by truck or block load, and then you put them in the storage, and then you dry them because you don't want to have high moisture. If you have too much moisture, it takes lot of energy just to evaporate the moisture. So you dry them outside, and then you mill them to small size, because if you have large size, takes a lot longer to heat up inside. So if you make it smaller, it can be heat up very fast, like within a few seconds it will be all carbon. So because of that, you have to mill them, and then you pelletize if you want, because they based on how you want to make the shape, final shape. And then you do, this is the critical method, the pyrolysis chamber. Pyrolysis means heating the any organic biomass without any oxygen, because oxygen will make it carbon dioxide. So the carbon will not be there in the solid. It will become carbon dioxide. You will only left over will be ash. So that's why anytime you burn carbon plus oxygen, you get carbon dioxide and ash, because most of the organic biomass is made of carbon as well as inorganic nutrients. And those inorganic nutrients become ash. All the carbon become carbon dioxide, but you don't want that to lose that carbon. That's why the key here is to not have any oxygen. So what you do is carbon plus nitrogen and extremely high heat so that it can burn. Okay, so then you have activated carbon, or let's say carbon, and some amount of ash, but not a lot. Okay, and now it's called carbon. Okay, so charcoal, that's how you produce charcoal. But the next is activation. Activation means anytime you form any carbon, burn them, there are a lot of fine particles in between. The ash will be inside those pores. So what they do is they use very high temperature steam, like a basically high temperature steam is a high moisture. It can retain high temperature, so that's why the high temperature steam, they pass through that. When they pass, all those pores will be unclogged, and so that means now these nano micro pores are going to be empty. So that gives them high surface area. So that activation step makes the charcoal as activated charcoal or activated carbon. And then you do cool, then you can do some kind of treatment. They do washing, dewatering. They sometimes wash with a highly acidic solution, HCl, to dissolve some of the ash, or to remove some of the fine residues. And they rinse and then dispose the ash. The rest of them you dry and send it as an activated carbon. So the idea here, what you learn is any biomass, any waste biomass can be used to produce activated carbon in this process. If you don't do any activations, then the things that you produce is biochar. Okay, biochar is produced up to this stage. And as you see, there are many steps are missing here. If you don't produce activated carbon, that makes the cost very low. Because in biochar, you don't have to increase the temperature to all the way to 1200 degrees Celsius. So as I said, this pyrolysis, no oxygen, and the heat would be greater than 1200 degrees Celsius. Okay, it's very high temperatures. But for biochar, you don't have to heat that high. Sometimes you can produce with a low temperature, like 500 degrees Celsius. That means it lower the cost to something so cheap that you can be used a large quantity. And so that's another way to also produce biochars for filtrations from all the organic waste. So this is another sustainability angles for many of the products that you are using. It can be used as a filter materials. Okay, so now that you learn how the system works, let's say how to design them. So this is how they look. If you see activated carbon treatment systems, you basically put on a trailer, and each one is one tank. And you see these are all in series. They are not in parallel, so series connection. So that means water comes in one end. Let's say this is water coming in, then the out. Okay, so it goes to here, then it goes to here, then it goes to here, goes to here. Okay, and usually these are fed from the bottom, not from the top, to avoid any kind of air getting into the system, because air can trap, air can reduce the capacity of activated carbon because it can block the surface. This is activated carbon. So when you design this kind of system, you got to think of how many of this tank you need, and how fast the flow rate should be, how much water you can treat in these systems. So these are the calculations as an engineer or scientist you have to come up with. So you'll learn that in next few slides how to do that. So as I said, contaminated water pumped from one end, usually bottom to keep the air out, and the effluent is fed into another tank filled with a gas, activated carbon. So the reason people use granular instead of powder is because powders can clog the system. So powder has high surface area, but it's not very good at pumping groundwater through it. So mostly GSE or granular, which means it's a bigger size, are used in the system. And so let's say what are the quiz question it can be, the concept questions. So most of the time your goal is to remove as much pollutant as needed. So there are certain things you could change. You could change number of tank, performance, let's say performance depends on number of tank. So if you have your performance will increase if you had more number of tank, but it also increase the cost, right? So that's one thing. Number two, it also depends on flow rate. Flow rate means how much pollutant you are adding to the system or exposed to the system. So if you think of, conceptually, if you add very high fast flow rate, that means water is moving very fast through the activated carbon. It doesn't, that means the pollutant or the activated carbon doesn't get enough time to absorb the pollutant. It takes some time for them to stick, right? So if you are moving through very fast, then the contaminant may not have sufficient time. So that means the performance will decrease if you increase the flow rate. So that means another way to say is if you decrease the flow rate, that means you increase the time for the pollutant to remain in the system long enough for them to be absorbed. And the third one, it depends on the types of granular activated carbon or the quality. Mostly it depends on the surface area, right? So GSC surface area. As I said, this is adsorption is a surface area active process, so that means it is going to bind more contaminants if it has higher surface area. The quality is higher. So usually another things to think of is how the quality is better. Mostly if you have high temperature, most of the activated carbons are standardized. So they are usually produced at very high temperatures. But nowadays, because of biochar production technology, a lot of times they also use different method. So if typically if you have high temperature, if you make more quality carbon. If you increase the temperature, you produce less and less quantity of activated carbon because you're more likely to burn something else. But the quality become more improved and more activation is and activated, it will increase the performance. So this is mostly quality. Okay. And a couple of things can also influence activated carbon treatment is also the type of groundwater you have. If your groundwater is very polluted, means it has lots of other stops inside it, that means those stops will compete with pollutants for adsorption. So that means if you have, let's say, more competing chemicals. So if you have more competing chemicals, that means the same site is going to be blocked by these chemicals. So that means your actual pollutants will not be efficiently removed. So these are the different products. Okay, so the conceptually you can think of. Now, there are some scientific or engineering terms that you are going to use. One is empty bed contact time. What does that even mean? Empty bed contact time means if you imagine you didn't fill the entire tank with no activated carbon and you just pump the water through it certain flow rate. So you want to know how long that entire water is going to be replaced. So basically it says how much time it takes to fill up the entire tanks with that flow rate, specific flow rate. So usually that's a way to say that how quickly you can treat as much water possible. So empty bed contact time is usually typically 5 to 20 minutes. This is the engineering definitions in the sense, this is a design definitions. Anything longer, it's too expensive because you are basically, not treating enough groundwater per quickly. Anything smaller, then it become less efficient because things are moving so fast that adsorption is not very efficient. So typically they use 5 to 20 minutes, roughly 10 to 20, 15 minutes is very common. 5 is too short already. 20 minutes is, that means you are not treating enough water per day. Everything else, as I said, contaminant types, basically look for how many number of carbons. So if you have more number of carbon, if carbon number increases in the pollutants, the treatment efficiency would also increase. The reason is, again, adsorption is more efficient if you have more organic carbons. Water chemistry, it says competing ions, pH, ions or salt. All these things can influence the adsorption. If you have too much salt, this will also interfere with adsorption. So if you want to improve the treatments, that means you want to have less salt in the groundwaters or less ions. pH is an interesting concept. It depends on whether your pollutant is ionic or not. If it's not ionic, then it doesn't matter. For instance, some of the chemicals has acidic functional group. For instance, let's say, as you say, if it is ionic, it's going to be more water soluble. That means it's not going to be removed very easily if ions are there. So that's why pH is a factor there. But again, I would not think too much about this pH for this class. Just know that this is a factor. Okay, so let's calculate some numbers here. Okay, so the one of the things you are going to calculate here is the empty bed contact time, right? So empty bed contact time is basically, let's say, right. I think I have another. Yeah, it's here. So the idea here is empty bed contact time means it sets how much time you have to treat certain amount of water. So this is another way to compare between different treatment system. And so the point is, that if you have slow, the time is higher, that means you have more efficient treatment technology, because that means you spend longer time in a tank. Then why people don't use very high amount of empty bed contact time? That means you are limiting how much amount of water you can treat per day. So that's, and also, so that means if you empty bed contact time, if it is increases, that means treatments will be much efficient, right? But you treat less water per day. That means you are not, because just using the system or is time is money, so that means you are not treating enough. That's one other aspect. But on the other hand, if empty bed contact time is lower, that means you are treating more water, but your treatment efficiency can decrease. What it means that you are flowing. This is the case when the flow rate is low. This is the case when flow rate is high. When the flow rate is high, you are loading a lot of pollutant per time. That means you are also exhausting a lot of activated carbon very quickly. So that means you have to replace very more frequently. So as I said, the empty bed contact time is basically 5 to 20 minutes. The way you can calculate is it's basically the volume of the tank divided by the flow rate. Flow rate is volume flow rate, which is equal to empty bed contact times, right? Normally that's how the definition, but why it is used? Usually empty bed contact time, you fix it, because that's how your 10 to 15 minutes. Once you fix the time, it also set how much volume of tank you need. That means these are the volume you are going to fill with activated carbons. So this is another way to calculate how much volume of activated carbon you need to buy. So this method is used if empty bed contact time is fixed, or the amount. Let's say you said as 10 minutes or assume 10 minutes, what's the flow rate from those groundwater well, multiply them, you kind of find out how much activated carbon you need per day to treat. So this is just another formula to understand how much activated carbon.
Quick question on that. Is it the like the total volume of however many tanks you decide to use, or the volume of an individual tank?
So volume of tanks, okay, each tank, and so that's a good point actually. So volume of activated carbon is volume of tanks, and then sum of, so that means you sum all together entire tank. Okay, that's because you fill with everything else. But if you are looking for empty bed contact time for each tank, then you have to divide that tank volume divided by the flow rate.
Okay, thank you.
The second thing you have to think of is how wide it is going to be, because that also determines how much water you can flow through it. So let's think of what's the dimension should be look like. Well, you can make it as wide as possible, but there is a limit to it. If you make it too wide, there is a problems. The reason is, if you see the way the tanks are designed, think of this. Let's say we have a small one, and then we have a bigger one. Okay, and usually these designs are like this. The reason is, I'll tell you why this design says conical. If you think of fluid dynamics, how the water flows, usually they're injected here. This goes like this. Okay, I'm going to make a different color so that you can see those. So this is water stream. Okay, so same thing here. If you see, because of the flow rate, it's going to be more likely going to go like this. And what happens is, most of the time, this corner area are kind of dead volume. The reason is the flow rate is not going to touch there. So that means these locations, you are going to have activated carbons, they are never going to be used up. So these are dead volume. Dead volume. So that's why you don't want to have very wide, because if you have too much wide, the way the fluid streamline goes, you'll have lots of dead volume. That means you all have lots of unused activated carbon. That's why I don't want to keep it much wider as possible. But if you want to know what's the activated, the height would be, so this is going to be, this is height. Height is basically volume divided by the area, surface area, or the area of the, this is the area. If you know the total volume, if you divide area, you will know the amount, the height of the system. So an area, if it is cylindrical, the area would be pi r square is the area of the circle, and times the height. No, that's the area. And the volume is basically volume of activated carbon tanks. So this is, let's say, why it is useful. If you know the loading rate, how much quantity of activated carbons or how much water you're going to treat, this says here 5 gallon per minute per square feet. That's usually people use. That's as a definition. So if you assume this one, it determines how much area it should have to treat that water. So again, these are basically normal range. Okay, so that doesn't mean that you have to fix with that one, but just know that most of the activated carbon, they use the around number about this. When we solve the questions, we'll see it. Okay, now the last thing is, how do you calculate the removal rate or the efficiency? So that's basically mass balance. So this is activated carbon tank, and your flow is coming in, the same amount of flow. This is for one tank, okay? And the same amount of flow going out. And you have some concentration coming in, this is very polluted, and remove a lot of pollutants, and the C out will be usually less than C in. So C out is usually very, very less than CE, because that's your goal. So if you think of treatment efficiency is basically um, the removal means, what's the coming in, mass of the total contaminant coming in minus mass of the, this is in, minus out, is total removed, divided by whatever coming in is removal, or R is the removal efficiency. Um, Removal efficiency. This is removal efficiency. If you multiply by 100, this is the percentage removal. Okay. So what it means that whatever pollutants coming in, this fraction of pollutants that's removed in the system. So based on mass balance, what you can do is the difference of concentration of mass coming in. So mass equal to, so if you see dm by dt removed, dm by dt in minus dm by dt out. And you know that mass of pollutants is concentrations time volume, right? That's the mass of pollutants. If you see dm by dt, usually concentration of pollutants in the influent effluents are constant after equilibrium, so you can take that out. So dv by dt, C times Q. Okay, so that's why if you see this number here, it will be Q times C in minus Q times C out. If you take Q out, C in minus C out, or Q times delta C. Okay. So this is the percentage, or the amount of pollutants removed in a system. So if it is a lot of times, as I said, C out is very, very small because you're removing a lot of polluted pollutions from water. So roughly you can, I would not assume this one, but a lot of times if you make this assumption, your answer is not going to change a lot. So this, I would say that if you assume C out is very low, if the number is given exactly what is C out, you don't have to assume that because you can calculate everything. But if not, then you can always equate C in times Q is the amount of pollutants removed. It just assume that everything is removed. So this is again simple mass balance based on CE153. But now the last thing you want to calculate is the amount of times you have to replace the activated carbon tank, or how quickly you have to change the activated carbon after it becomes exhausted. This is the one that is more important for any engineering calculation. So first thing you have to know is what's the capacity of how much pollutants that's normally removed. Okay, so let's think of this R means the R that we calculate here. It means that amount of pollutants removed, and this is the amount of pollutants removed if you just know C in and C out. And then if you want to know what's the amount of contaminant adsorb, it should be the equal to the same thing, right? So that means if you want to calculate amount of pollutant removed, means this is removed from water, then you can assume that all of them must have gone to the to the organic to the activated carbon tank. So amount of pollutant adsorbed is basically the concentration of pollutant on activated carbon times mass of activated carbon. Okay, I just write GSC. So concentration times mass, because concentration is usually contaminants in activated carbon is usually contaminant mass divided by mass of activated carbon. That's the unit. So if you multiply that, you must get the amount of pollutant adsorbed. So this ratio is the ratio of that. Usually normal time, you can say that this should be equal. But a lot of times you don't wait for the last moment. The reason is if you wait for the last moment, so already you are getting the polluted water. So that's why you have to replace that before all the pollutants are absorbed. So that's why the change out frequency is the ratio of that. So this ratio, the amount of pollutants absorbed divided by pollutants removed. This ratio. And so that amount, this concentration of pollutants in activated carbon, you can get from isotherm. The friendly or linear isotherm, if you remember that one, C in Q or concentration of contaminants in activated carbon, here is written as Q times Ma. So this Q is KD C water on aqueous concentrations. If it is linear absorption, if it is friendly absorption, you remember this Q equal to C to the power 1 over N. Okay, this is if you assume friendliage. So these are the things. If you have isotherm, you will be able to calculate this Q from these equations. And again, this C aqueous or C concentration is the effluent concentration or C out. This C not C in is specifically how much pollutant remain after absorptions. So this one is actually solved in C153, but it's not in the complex way you didn't really calculate the activation carbon tank. So let's solve this question, then we'll have a break for 10 minutes. So this is one question on your homework. So I already released the homework. It's not due for until a couple of weeks. So I'm just going to show you the questions. Let's see. Okay, so this is the homework questions. This question is very similar to the example that I'm going to solve now. And basically you are given a concentration in and out, and then you are going to design the activated carbon tank based on the absorption capacity of the activated carbon tank. So let's get to that. So let's see where it is. Okay, so let's read the questions. It says that dewatering to lower groundwater level for below ground construction is often necessary. At a construction site, the contractor unexpectedly found that the extracted groundwater contains 5 milligram per liter of toluene. So this is the concentrations in, that means this is C in, okay? C in is 5 milligram per liter. The pollutant is toluene, that's the name of the pollutants. You can search what is that structure look like. The toluene concentration of groundwater has to be reduced to below 100 ppb, below discharge. So that means it says the C out. C out has to be 100 ppb. 100 ppb. Again, parts per billion is same as, because in water, you can assume that's 100 microgram per liter. Okay, so this is 100 microgram per liter. So that means this is 0.1 milligram per liter. You want to have same units. That's why I change it there. And to avoid further delay of the tight construction schedule, off the shelf 55 gallon activated carbon units are proposed. Because you have, typically you can get 55 gallon tanks from Home Depot or other places. This is a very standard design. In fact, in UCLA, if you want to get the maximum amount of tank full of pollutants, you get the biggest tank is 55 gallon. This is a standard size. I don't know why that comes out. It's just like there are certain size you can buy. 55 gallon is a very standard one. So what they do is they get that the tank and they're going to fill with activated carbon. So that means each tank size is 55 gallon. That's the volume of activated carbon you can fill in one tank. Use the following information to design and activate carbon treatment systems, including number of carbon units, means number of tank, configuration of flow, means now how it will flow, the series or parallel, And the carbon change out frequency means the number over here, T. How frequently you have to change the frequency. So there are things given: wastewater flow rate, this is Q, okay, and gallon per minute. So that's then the second one. So let's say this is 30 gallon per minute. That means you have to change to 1 gallon is 3.785 liter, because everything is liter here, so you have to change it to similar unit. Diameter of the activate the carbon packing bed in each 55 gallon is 1.5 feet and 3 feet is the height. So it says the 55 gallon tank, 55 gallon tank, it says this width is 1.3 feet, this width is 1.5 feet, and this is 3 feet. So that means it gives you height, and that means you can also calculate area. Okay, the diameter is given, height is given, you can calculate the area also based on that. Bulk density of activated carbon is 30 pounds per cubic feet. What is bulk density? Bulk density means how closely you are going to pack the entire tank with activated carbon. So when you pack, it means that mass of activated carbon divided by volume of tank, volume of packing, okay, wherever you pack. Okay. So that means if you know bulk density, if you know the volume, you also can calculate how much activated carbon you can pack inside based on bulk density. Adsorption isotherm is given Q equal to this. So that's basically this Q value is given. And it says friendly, it's whatever the isotherm, it's a Langmuir isotherm based on how it is written. It doesn't matter because it's already, so that Q equal to, the unit is important, kg of pollutants divided by kilogram of activated carbon. 0.04 times CE divided by 1 plus 0.002 CE. And this CE is the concentration of pollutant in the effluents after adsorption in milligram per liter. So this CE is here. Okay, effluents, what's coming out. All right, so that means everything, whatever this given, I wrote everything else. So now question is how to calculate the size. First thing you have to calculate, let's see, determine the design of activated carbons. First thing you have to do is what's the capacity or the Q. Q is given here, so you can use that calculations to calculate. So the Q would be, if you calculate 0.04 times CE, which is 0.1 milligram per liter, 1 plus 0.00, the value. Whatever that number, you'll get kilogram of toluene per kilogram of activated carbon. So that means it's the amount of toluene that can adsorb per 1 kilogram of activated carbon. Determine the required volume of activated carbon. So that's basically how much activated carbon you need. Based on, as I said, there are multiple ways to calculate that. One way to do is, as I said, the volume is replaced by this one. Volume of activated carbon is equal to Q time if EBCT, or the activated contact time. If you assume something, then you can find that value. So let's assume that this is just one way. Let's assume that empty bed contact time equal to, the assumption you can have something between 5 to 20. So you can pick any number, but roughly, as I said, 10 to 15 is a very good average. Too high is too expensive, and too low is going to be less efficient. So that means let's assume, I'm just saying that now, you can assume 10 to 15. Let's assume in between that 12 minutes. This is assumption. If you assume this one, the volume of activated carbon should be m 12 minute times the flow rate. The flow rate is given here. Whatever that number, you should be able to calculate that. So that will give you the amount of the time required for the water to stay in one tank. Okay, so if I do this one, write this value. So 12 minute times 30 gallon per minute. Again, 1 gallon is 3.785 liter. This right, gallon per minute. Okay, and then you can also do another way to do is let's see, all the questions here are in feet. So instead of converting liter, you can also convert everything to cubic feet. Just see how much gallon is per feet. That's another way to do it. Determine the required area of activated carbon adsorption. So that's based on the, if you see, I think all these equations are given. So you just have to plug those values. If you know the surface loading rate, 5 gallon per minute, you should be able to calculate the area. So all that, what I'm going to do is let's take a break for 5 minutes because it will take long time to solve it. Just start plugging the value and getting the answer. So I don't want to waste a lot of times working on the actual which is formula given. So what I'll do is I'll write all the equations and everything in the final annotated slides so that you can check if you have questions. Again, a lot of these are based on assumptions, so whatever you assume, it can change. If you don't assume something, still you can solve it based on that equations. So I'll write all these in the examples, and that way you can follow through. But basically, you already know what's the concept here. Everything is given. You just calculate the value based on these equations. So let's take a break until 5:15, and we'll be back. In the meantime, I'm going to write the solution here. Okay. I'm going to stop sharing or stop recording or pause it. Okay, so it has multiple steps. Basically, it asks you to calculate the amount of volume of adsorber activated carbon. It also asks you what's the height of the activated carbon tank should be. It's also asks the removal rate. It asks the how much amount of activated carbon any a tank can hold. That's basically volume. It asks the service time. It also asks the different configurations based on how much area you need, all that. Because your assumptions are already given here, right? So you're basically for efficient treatment system, you have to assume that the surface loading rate or the amount of water that goes to each tank will be certain amount of rate. For instance, it says what is the surface loading rate? That's 5 gallon per minute per square feet. It means that you can apply only 5 gallons of water per square feet of activated carbon. If you have add too much, then obviously the activated carbon tank will not have enough time to process it. That will also maintain whether you can push water as fast as possible or not. So these are certain things you assume that these are the number you want to fix. So this is one assumption. Surface loading rate is around 5 gallon per minute. You typically want to do as much as possible because that way you can treat as much water in less time. Another is empty wet contact time. For in this problem, we assume around 12 minutes. You can do assumption at 10 minutes, all that doesn't matter. But one of them you have to assume. So you have all these equations. These equations mean something. So as long as you understand the concept, all you have to do is plug the equations and get the concentrations. So I did that one. The very first one, adsorption capacity. You have the equation Q, you just plug all the value. It says, if you do all that, it says the answer will be 0.1 kilogram toluene per kilogram of activated carbon. The units are similar, so you can also say this is same as 0.1 pound of toluene per 1 pound of activated carbons. Okay, it's the ratio is 0.1. Okay, it's the mass. So you can do as long as you change the same unit, it's equivalent to same. The second one, I calculate the flow rate. Flow rate is given 30 gallon per minute. I change to square feet or cubic feet per minute because many of the units that you see over here are in feet. Everything is in feet, so I changed to cubic feet just to make it easier to calculate. So that turned out 48 cubic feet per minute. And then it asks what is the total amount of volume of activated carbon. That's volume is flow rate times empty bed contact time. So you calculate the flow rate, which is 48, and then you have 12 minutes is the assumptions on the empty bed contact time. That will give you the total maximum amount of activated carbon you need to treat this pollutants. The third question was determine the required surface area of activated carbon adsorption tank. So the area is again related to how much loading, how much you can pour. So that's, as I said, area is flow rate divided by surface loading rate. Surface loading rate, you cannot make more than 5 gallon per minute per square feet. That means this is fixed. So once you fix this one, you know the flow rate, you get 6 square feet. It means that the entire activated carbon has to spread across 6 square feet. Okay, that's where you can pour 30 gallon of water on top of it. But you know that you don't have luxury of having that 6 square feet of a tank. You cannot design it because there is no tank with a area 6 square feet. All they got is a drum with a 55 gallon. That means you have to arrange them such a way that they all add up to 6 square feet. So that's what I did. I calculate the drum area 5, which is pi r square. That's the area of any circle. So each drum is 1.5 feet is the diameter. So if you plug this value, you get 1.77 square feet per drum. That means each drum has that much square feet area. Now you have to add them all to become 6 feet because that's the maximum square feet you need to design. So you just have to you divide 6 square feet by 1 point each drum area, you get the number of drum you need. And it turned out it become 3.4. Well, you cannot have a fraction of drum, so that means you have to replace it to nearest next number. That's why it become 4 drum. So what does that means? It means that you have to pack 4 drum and arrange it such a way that you put entire 4 gallon of water through that 4 drum on 30 gallon. So you divide that into 4 different divisions. So each flow is going to go to that 1 drum each. Then if you do 4 gallon, then the actual area would become 4 drum times 1.77 square feet is the actual area of the each drum. So that means the real area right now is 7.08 square feet. That's the amount of activated carbon area. Now you are looking for 6 square feet. That's the minimum. But because your drum is constrained, you cannot meet that one. The nearest you can meet is 7.08 square feet. But that's determine how many activated carbon you can arrange like in a series in a parallel. What you don't know is what's the height would be. That height again depends on, as I said, volume of activated carbon divided by the area of absorption. So the volume is total volume is now 48 square feet. That's the one you calculate very early. This is the one. And if you divide that entire volume divided by the area of the things that all the 4 drums, you got 6.8 um, feet. So that means this is the height of activated carbon tank. Each tank should be, but 55 gallon is only 3 feet tall. So that means you have to think how many 3 feet you can arrange such a way that it becomes 6.8 feet. So if you divide 6.8 by 3, it becomes 2.3 drum. So that means you have to have 2 drum plus a little bit extra. Well, you cannot fill any drum. So that means you have to fill to the nearest number. So that means you got 3 drums. So now what does that mean? It means that you can arrange four different activated carbon tanks in the parallel like this, and then you can stack them up at least 3 drum to achieve that height, 6.8 feet. So now this is the arrangement. So you have 4 drum, each drum um, three drums side by side like up, so that you can post through that one. And then you have also four drum. Each flow rate bifurcate, or each flow is divided into four different flow, equal volume. Each one goes to one stream. So this is the arrangement you get. So four row and three columns, so 4 by 3. 12 drums you need total. If you know 12 drums, you fill onto, you know each volume, then you know the total amount of real amount of activated carbon you need. Then the question was, what's the removal rate? Removal rate is the effluent concentration times the flow rate. That's assuming the effluent is very low. So that if you plug the value, you get the answer just by calculating. The number 7, if you see the equation, it says determine the service lifetime of activated carbon adsorber. So basically, you got to say how long these pollutants will before you have to replace. Um, so that's based on M, total amount of contaminant removed divided by removal rate. So total amount of contaminant removed is the formula is concentration of contaminant in activated carbon times the amount of activated carbon. So we put that value, then you times amount of activated carbon is volume times the density, because you pack them inside those 12 drum. So that's all you did. So Q value you already know, 12 drums, because that's what we arrange here, 12 drum times the each drum volume. And then just because you have this much volume doesn't mean that that's the entire field is activated carbon, because when you pack there are airs. So that accounted by the bulk density of that packing. So when you combine those all together, it gives you this number. So it says this much amount of toluene you remove. But then you know the removal rate is 1.8 pounds per day. So if you divide that, that means it takes 6.6 days to exhaust entire activated carbon tank systems. So that means you have to replace every 10.6 days at least the entire system. So again, these questions are solved already in the handouts in the book. If you, I upload a book so that you can, not book, the handout. So you should read them so that you know each steps and understand it. And exact same question will be in the homework, and also the midterm questions are very similar to homework. So you should at least try to solve this particular problem. So the possible quiz question for carbon adsorption is, how do you slow down the exhaustion rate of tank? So think of how do you slow down the exhaustion rate. So any discussion here? Exhaustion means, if you add more contaminants, obviously it's going to exhaust quickly. So that means you have to slow down the amount of contaminants you add. So the way you can control that is the Q. If you decrease the flow rate, then means if you are adding less contaminants, so that means it take longer. Or another way to slow down the exhaustion rate is you add so much activated carbon, it takes long time for them to get exhausted. So how do you add more activated carbon? Well, you can increase the height, you can increase the area. So all those things you can say. You can increase the area, you can increase the height of each tank, or you could, which is basically means you can increase the volume of tank. Okay, if you increase the volume, you have more activated carbon, so that means it takes a lot longer time. That's one way. Other things you can do is you can also pack lots of activated carbon in a one tank, which is bulk density. If you increase packing, you will also decrease the exhaustion rate. So you should think all this conceptual way. That way you will be able to answer those questions. Which operational parameters can affect removal and how? So think of a couple of things you can change, right? So these are the things you have to think. What is the operational parameters? So let's say you want to increase removal. That's your goal. Okay, this is your goal. So then now, point is how you can actually control that um, removal. So there are a couple of things. Removal is Q C in minus C out. That's the, if you don't assume. So there are a couple of, so you can change it. Increase the removal if you let's see, QC in, Q out. So here is the trick here. The removal is, this is the mass. Now, point is how you actually decrease C out. That's the whole idea. If you decrease the C out, that's the only way you can change. So your goal has to be, because C in you cannot control because that's the amount coming in. As much as you can decrease, then the removal will increase. So C out is means you are removing a lot of contaminants so that very little remaining. So efficiency depends on, again, everything that you know. Ball density. If you pack a lot of activated carbon, more surface area, more it's going to adsorb. So that means to increase this packing. Exact same thing. Increase the volume, you are going to treat a lot of, remove a lot of pollutants. Increase the activated carbon quality, you are also going to decrease the effluent concentrations. Another thing is you can do is the particle size. If you decrease the particle size, there are more surface is going to expose to the pollutant. So that means more and more is going to adsorb. So that's the what happened. Particle size decrease, that means you are going to increase more surface area and more absorption. So these are different things you can think of, conceptually. All right, so I guess, we will not have sufficient time to solve question on air stripping. So I'm going to explain the concept, and either I'll solve the question next class, or I'll just upload the solutions. So air stripping is a very simple concept. It's if all you the concept is the water has pollutants. They are volatile. That means they are finding a ways to come out of the water. The only way they can come out is if the bubble size is so small that they have a more easier to cross that air water interface. So that's why you have to just add the water on a location. Either make a mist out of it, or you can put just trickle on a packed media so that it just the air is going to be exposed to that pollutants. So that's what it works. So you have basically water, contaminated water injected, and then air is pumped. Clean air comes from bottoms, and contaminated water comes from top. Okay, and then they trickle through the things, and that way their air, the contaminants move from water to air, and then the polluted air is captured from the top. Okay, so if you see, this is how the mass balance works. So basically you have polluted air, and the this is the contaminated air coming out of the system. You are injecting polluted water, and you are injecting, or you are getting clean. This is clean water, this is polluted water, groundwater. So this is clean air, this is polluted air. Okay, and then you capture. So that's how the whole exchange happen inside. So if you see what happened exactly in that small bubble is you have polluted contaminant. So this is C in, where the contaminant concentration in water. And then these pollutants you will diffuse out of the air. And so this is the concentrations of contaminants in air. G out is the concentration. That way you know this is in air. G for gas, C just we use the notation for the concentration in water. So if you do mass balance, the amount of contaminants removed from water must be going to the air. So that's what we write here. Flow rate of water times the concentration changes in water, C in minus C out, equal to the amount of airflow times concentration of contaminants in air out minus in. So roughly you can say that you usually inject the clean air, so that means concentration of pollutants in that air that you inject is nothing. So this you can say nearly zero. And similarly, you can also say that your goal is to remove all pollutant from water. That means C out will be almost nearly zero. That means all the pollutants are removed from water. So if you do this one, this equation become Q C in equal to QA G out. So So these are concentration in gas versus water. So if you think of this value, if you make this answer, so this is let's say um, QA by Q water. This is Q water. If you rearrange this one, this will be QG out divided by C in. If you take the ratio, it should be 1. What does that mean? Now, if you know this is the ratio. If you see this second term, this is the concentration difference or the ratio of concentration in what gas to air. That is actually a thermodynamic constant. That's Henry constant. So if you plug this value, Henry constant of any pollutants, time the flow rate, it should be at least 1, okay, for this to work. If it is obviously, if it is more than 1, it's going to work efficiently. If it is less than 1, it's not going to work as efficiently. So this is the design formula. The minimum amount of this one should be equal to 1 for this to work. And this factor is we called stripping factor. So this entire number, this one, we call them as stripping factor. So your entire design is based on this particular formula. So S equal to Henry constant times QA by Q water. So that means your ability for this treatment system to strip any pollutants depends on Henry constant. So if your Henry constant increases, obviously you will more strip out of more pollutant. That means if the more volatile pollutants, it's going to strip out more pollutants. And then another thing you see, QA by Q water. So that means if you pump air much faster rate, you are going to take more pollutant out of the water because you have more air. That means it's more likely to that gradient will be much higher. So the more likely this pollutant will get into air. Same thing if your water flow rate is low, the stripping factor will be low because it takes a lot longer for this to pass through the system. Typically, you don't want to have very high flow rate. If you make too high flow rate, air flow rate, you are going to blow entire water into the outside. So you're not going to really let the water come in. So that's why there is a control. You can't have very high flow rate of air. So typically the design for S should be between 2 to 10. If you make it too high flow rate, as I said, if your S is very high, that means you are blowing air so fast you are putting a lot of energy. That means that energy is expensive. And second, you may actually flood in the top layer because the water cannot trickle down as fast as possible. So this is the concept. Okay, so that's all you need as far as concept is concerned. And now question is, there are a couple of things. A pollutant can move out of the water because of a lot of different reasons. One is the exchange rate or the mass transfer rate. Mass transfer. That mass transfer rate is a lot of times depends on what kind of these beads that you put, because these beads what they do is they makes the area much higher for the water to trickle around it, so that the mass transfer rate will be higher. And mass transfer rate also depends on how volatile this pollutant is, like Henry constant. So these are all different factors you can think of. So there are equations that I'm going to show you next. I think you should read the handout. This is the concept. This is all the concept needed, and then everything else is the um, is the um, is the solving the problem. So let's see. There's an example. I'm going to solve it quickly. It says a packed column air stripper is designed to reduce the chloroform concentration in the extracted groundwater. So chloroform is the contaminant. So that means if you know this one, you will be able to find the Henry constant if you search online. The concentration is to be reduced from 50 milligram per liter to 0.05 milligram per liter. So that means your C in is this. This is C in. This is C out. Okay. Determine the minimum air to water ratio. Minimum air to water ratio, which is and the design air to water ratios and the design air flow rate. Design air flow rate is basically Q air, and design air to water ratio. So basically these are the ratio QA by QW. All those factors are asked. So let's see. Now stripping factor is given this one, which means you know H times G out divided by C based on this value over here. No, I'm sorry. This is not a right answer. So this is Q air divided by Q water. This is Q water. Henry constant is given 0.128 atmospheric. So this is you see, this is a partial pressure. So that means you should know how to convert Henry constant. So search online. These are all in the um, in the C153, how to convert Henry constant from one unit to another. So I'm going to show you here. Just if you don't know how to do it, you can calculate the other way. So this is by gas law constant. Okay, Henry constant in pressure. You can calculate based on, this is by pressure. So it would be dimensionless Henry constants times R. R is gas constants times temperatures, and all these. This is specific gravity of water. W is the molar weight of water. So these are all given actually in the handout. So if you don't understand here, the handouts I give you has those numbers or formula. So ultimately, this is molar water weight. Means if you think of water, hydrogen is 2 plus water is oxygen is 16, so that's 18. So that's 18 come here. So you should read that handout so that you know how to use this formula to calculate the Henry constant, H prime. So once you do the H prime, you should be able to calculate all these value. So example solution, the region dot rate is QAL times this ratio is asked you. This one was asked. Okay, so if you see times Henry constants, that's the stripping factor equal to 1, right? So if you do this one, Q air divided by Q water should be 1 over Henry constant. And that value over here is 0.098. So that will be 10.25. So that means this is the ratio of the flow rate, air flow rate by water flow rate. And you know that stripping factor, which is equal to 3, is Q air divided by Q water times H prime. Okay, this is another way to calculate. And then you know the Q water, right? Q water is 120 GPM. So if you plug this value over here, you should be also calculate Q air. That way, if you plug this value over here, I would calculate Q air is 3 times Q water divided by Henry constant. So if you plug all these values, you should be able to get around 30.75 gallon per minute. Not that one. Actually, this is Q air by Q water. 3 divided by Henry constant will be 30 because Henry is this equal to 0.098. If you plot that value, you'll get this one. So that's another way to calculate. So once you do this one, so this is for the minimum amount of, this is the minimum value needed. If you want to make it more efficient, this has to be greater than 1, which is in this case, it's already given 3 here. So based on that, you will be able to calculate the other value. If you know the ratio, Q water is given, then you know the air flow rate. So I don't want to rush again for this one because it takes a little bit more time for you to assimilate. So next class, we will solve this one. So I would say that let's end this class here. I'm going to, next class, I'm going to solve this problem, particularly how to design or solve the example questions. It will take 10 minutes, so I don't want to rush it today. Any question? But he has almost like a timer. He knows when I have classes ended. He's also bored, like you guys are now. 2 hours is too long. Okay, I'm going to stop recording.